Balance a ruler on your fingertip and slide your finger along it. Most positions fail instantly. The ruler tips off one side. But there's one exact spot where it sits perfectly still, as if held by magic. Why does an object care so much about exactly where you support it? Here's a fact you already know. Gravity doesn't just pull on one part of an object. It pulls on every single particle inside it. Every atom in that ruler has its own tiny weight pulling straight down. Add up all of those tiny downward pulls across the whole object, and you get one single quantity, the object's total weight. So if gravity is tugging on every part of the ruler, why does it only balance at one particular point, the midpoint, and nowhere else? That single successful spot is a clue. It suggests that even though weight is spread through the whole object, it behaves, for balancing purposes, as if it were all squeezed into one location. Now picture an L-shaped piece of card, like a thick capital L cut from cardboard. Before reading on, predict. Where would you need to support it so it balances perfectly? Is it somewhere in the middle of the visible card? Or could it be somewhere less obvious? Physicists give that special balancing point a name: the center of gravity. It's defined as the point through which the entire weight of an object can be considered to act. It isn't a physical thing you could touch. It's a mathematical stand-in, a single location that represents the combined effect of every downward pull happening throughout the object. Here's why that point matters for balancing. When you support an object exactly beneath its center of gravity, the weight acts straight down through that same support point. So there is zero resultant turning effect, nothing left over to rotate the object one way or the other. Move your finger even slightly away from that point, and the weight now acts along a line offset from the support, creating a turning effect that tips the object over. Picture an irregular, oddly shaped lamina, a flat sheet, hung freely from a single pin pushed through a hole near one edge. A plumb line, just a thread with a small weight tied to the bottom, hangs from that same pin. Because the thread hangs freely, it always settles into one direction, straight down, tracing a vertical line through the pivot point. That plumb line gives you a practical way to actually locate the center of gravity. Suspend the lamina from one hole, let it settle, and mark the line of the thread across the card. Then suspend it from a second, different hole, and mark that line too. Each marked line passes through the center of gravity, so wherever those two lines cross is the center of gravity's exact position. A third suspension point, if you use one, should cross at that same spot, confirming your result. It's tempting to assume the center of gravity must sit somewhere inside the solid material of an object, right in its visual middle. Test that idea on our L-shaped card. Because one arm of the L is missing material, the balancing point, calculated from the plumb lines, can actually land outside the physical shape entirely, in the empty space of the notch. The center of gravity marks where the weight effectively acts, not where the material happens to be. Now try a different comparison. Stand a tall, narrow cardboard tube upright, and stand a short, wide box next to it. Give each the same gentle sideways nudge. Which one topples first? The tall, narrow tube goes over with barely a touch, while the short, wide box barely wobbles. Two features of an object control this difference: how high its center of gravity sits, and how wide its base is. An object with a low center of gravity and a wide base is described as stable because it resists tipping. An object with a high center of gravity and a narrow base is unstable because a small push is enough to send it over. The precise trigger for toppling is this. As you tilt an object, the center of gravity moves too. The object stays balanced as long as the vertical line drawn straight down from the center of gravity still lands somewhere inside the base. The moment that vertical line passes beyond the edge of the base, there's nothing underneath to support the weight anymore, and the object topples. Picture a diagram showing that same object tilted at increasing angles, with a dashed vertical line dropped from its center of gravity down to the ground. At a small tilt, trace that line. Does it land inside the base outline or outside it? While the line still falls within the base, the object's own weight creates a turning effect that rotates it back down to its original position. Only once the tilt is large enough that the line crosses outside the base does the object keep rotating and fall over completely. Apply this to something practical. A low, wide sports car taking a sharp bend, compared with a tall, narrow van taking the same bend at the same speed. Which vehicle is more likely to tip during that turn? The sports car's center of gravity sits low and its wheelbase is wide, so the vertical line from its center of gravity stays within its base, even as cornering forces push it sideways. The tall van, with a higher center of gravity and a relatively narrow base, reaches that critical tipping line far more easily. Before moving on, try recalling this without looking back. What exactly is the center of gravity? And what's one essential step in the plumb-line experiment used to find it on an irregular lamina? The center of gravity is the single point through which an object's entire weight can be considered to act, and you locate it experimentally by suspending the lamina from at least 2 different points and marking where the freely hanging plumb lines cross. Put the 3 pieces together, and a single picture emerges. The center of gravity is the point representing an object's whole weight. You can locate that point experimentally using suspended plumb lines on an irregular lamina, and once you know where it sits relative to an object's base, you can predict both whether it balances and whether it topples. A low center of gravity over a wide base resists tipping. A high center of gravity over a narrow base invites it. Next time you see a crane, a table lamp, or a double-decker bus, ask yourself where its center of gravity sits and how wide its base is beneath it. That's the compact rule that lets you judge stability at a glance.